Welcome in our new video for Geometrifying Trigonometry. In last 3300 years, we were all trying to find any axiomatic definitions of structural elements of trigonometry and functional elements of trigonometry, because trigonometry is now a 3300 years practiced subject, and it is very effective subject. In recent time, we have crossed the time of large language model, where we can handle human talks, human writings, and we can automatically generate big thesis papers also on very deep kind of analysis on written documents. But still now we have nothing concrete in hand with which we can convert trigonometry expressions into geometric objects. But we all know that from the day one of trigonometry, it is actually a subject of triangles, and trigonometry subject was designed to handle the properties of triangles, to solve the problems of triangles. But there was no concrete canonical formalization systems for trigonometry, and still now we have no direct computational model other than geometrifying trigonometry which can convert trigonometry expressions into geometric forms, like such that we can handle the trigonometry expressions and can visualize things like Euclidean geometry objects. And it is a long time dream that computers can automatically generate geometric objects from reading of trigonometry expression. We computer scientists call it as the functional programming on trigonometry expressions. We want some theorem provers which will automatically read the trigonometry expressions, and it will generate different geometric arrangements for different values of theta, for different values of angles provided. And in any trigonometry expression, several number of angles are discussed, and these all different angles which are present inside any trigonometry expression. Suppose they are alpha, beta, gamma, theta, alpha plus beta, beta plus gamma, gamma plus theta. In that way, those things are present inside the bracket of cos, sine, tan, sec, cosec, cot. Whenever these terms, like any expression which represents any angle, we consider it as a number which represents some angle either in degree or in radian. But it talks about a triangle. Obviously, when any single element, any single ratio of trigonometry is given, like cos, sine, tan, sec, cosec, cot, then we can think that yes, one triangle is there. But how many triangles should be there when multiple such trigonometry ratios are multiplied? When multiple such trigonometry ratios are multiplied, those are taken as the factor multiplication, and in these cases only one triangle is not there. More than one triangles are there. Sometimes one triangle is there and all the story is going around inside the one triangle. Sometimes we see that we cut the triangle into pieces and straighten it to form a line segment, and then we do the operations on that. But when we do what kind of things, the visualization system is not formalized yet. Geometrifying trigonometry is the only subject right now at the time of large language model processing and computational functional processing is going on. Artificial intelligence is still not mature enough to generate the geometry out of trigonometry expression, and Sanjana's geometrifying trigonometry is the only solution right now up to end of 2022, which is the only solution in world right now which can computationally generate the geometric pictures out of trigonometric expression. Now we are trying to generate exhaustively all possible geometry out of any given trigonometry expression. So it is very high time, it's a very important time when we should identify the structural properties of the elements and functional properties of the elements used in the trigonometry expression. It should be very much crisp to understand the structural nature of trigonometry ratios and functional nature of trigonometry ratios. We should understand very clearly the structural elements of trigonometry expression and functional elements of trigonometry expression. First of all, we have to understand what structural element mean and what functional element mean. The structural elements are the data structure kind of things. With real numbers are also data structures, complex numbers are also data structures, quaternions are also data structures, vectors are also data structures. And before 1860 there was no such direct involvement of vectors, because after quaternion came in 1843, after Hamilton made it, the quaternions placed an important role after complex number, and then the idea of vectors came out, which is the extension of complex numbers, and real rigid understanding of vectors started after the Gibbs book in 1870 end, and it took the maturity up to 1920. So it is very much important to note that before the vectors plus minus into divide with the things, we were not very much, the mankind was not very much in the strong position to use vectors properly. Even before Arthur Cayley's work on the matrix algebra, the concept of locked sets and the multiple elements, multiple numbers are locked inside an array, and they are interrelated to generate some meaningful algebraic structures, and these kind of formalizations were not clear before in 1880, 1890, and so it took 100 years more to delve into the deeper subjects to convert trigonometry expressions, which are like strings, and the parsing mechanisms to read the trigonometry expressions and to split it into the pieces, and to get the structural units first and to get the functional units, and then the operations can start on. After long research of 30 years, Sanjanath has found that trigonometry expressions are, and Sanjanath is working on the finite element analysis with the Delaunay triangulations, with Voronoi diagrams and structural analysis, and designing of many bridges and many buildings and architectural drawings, and with the triangulation operations and for many GPS systems. And after working with several kind of data structures for a long time, for building information modeling systems and for bridge designing systems, and for, as a 20 years experienced person from CAD programming world and Tekla API programming development systems, for the Blender developments and for triangulation mesh developments kind of things, after working on these kind of things, it was much clearer now that for trigonometry expressions we have to understand the structural units and the functional units first. And to do this kind of research, Sanjana found that every triangle is a number and every number is a triangle. We should explain it in very clearly here, that how a number is a triangle and how a triangle is a number. There was a previous video in which we have explained these things totally clearly, but again I should give a brief overview of this, how a number is considered as a triangle. First, we should understand that what a triangle do mean. A triangle has 3 line segments. One is the input line segment, and another is the output line segment, and the third line segment automatically generates, that is the complement line segment. There is a special video on that which explains this process. First of all, everyone should understand that triangle is made up of, any triangle is made up of 3 line segments. One is input line segment, another is the output line segment, and another is the complement line segment. These 3 line segments form a triangle. From now on onward, we will understand the triangle in this way, because these are the structural units of geometrifying trigonometry, and they also play a very important role for the functional properties of the geometrifying trigonometry. One more thing we have to make crisp, that there are 3 points also. The universal name of these 3 points are the pivot point, the stretch point, and the nodal point. Why should we name these universal names? Because many theorems in geometrifying trigonometry involve the specific names, where pivot point of one triangle overlaps with the stretch point of another triangle, and that has a deep theorem, and that is useful for the geometric graph theory. That is a separate domain, and for network analysis and for GPS systems, and for triangulations of the Delaunay triangulations for the finite element analysis, we can transmit the forces through Kirchhoff's law using this kind of overlapping nature of the points. So it is very important to axiomatize trigonometry geometrically, we have the specific names for the points also. Now on onward, we will not think that any arbitrary names ABC for the points is not a good practice, because while a subject is getting concretized and when any canonical axiomatic formalization is going on for any subject, we should have the very specific universal name for everything. So we repeat that 3 lines of any triangle are represented as one is the input line segment, one is the output line segment, and another is the complement line segment. All of these names are very important for geometrifying trigonometry. I repeat again, there are 3 points that have universal names. A pivot point where the seed angle is formed. For any triangle, there are 3 angles. One is the maximum, one is with the maximum internal angle, that is normally for right angle triangle it is 90 degree. One is the minimum valued angle which is forming at the pivot point, and there is another point that is the complement point, that is the 90 minus theta kind of thing, which is forming at the point which is called the nodal point. So for every theorem there you will find this kind of terminologies: the pivot point, stretch point, and the nodal point. These are very important terms in geometrifying trigonometry. So 6 terms for 3 universal names for 3 line segments. There is the input line segment, output line segment, and the complement line segments, and the 3 universal names for the 3 points are the pivot points, stretch points, and nodal points. There are well defined symbols for all these 6 parametric objects. And theta is the seed angle, 90 minus theta is the nodal angle. Seed angle happens at the point of the pivot point, and there is a maximum angle where for normal right angle triangle that is a 90 degree, and it forms at the stretch point. So all these 6 terminologies are very important to understand in geometrifying trigonometry, because large number of theorems and deeper understanding, even the machine learning systems also follow these names. And Sanjanath is preparing the TensorFlow model for this geometrifying trigonometry. Large number of data sets are under preparation, and all these data will come up with these kind of nomenclatures. So if you don't follow these nomenclatures, then you can feel odd when you will read any theorems, or when you will try to solve any problems in geometrifying trigonometry, or whenever you will try to call the API of geometrifying trigonometry made in C#, Python, or in Java. Then you will face problems if you don't follow these nomenclatures. These are the universal names for the 6 elements, which are most fundamental structural units for the geometrifying trigonometry processing. These are the structural units. You have already understood that for points the x, y is sufficient for the 2D planes, and geometric figures on the 2D planes and the Euclidean geometry on the 2D planes are the most fundamental way to analyze the trigonometric problems. And from 3300 years, the trigonometry is handled with the 2D problems only, and 3D problems came much later on. So we will first focus on the 2D problems only. Now we will describe a little about the concept of structural properties and the functional properties. But before that, we should tell that every number, every real number which has 2 types of conditions, that is the rational number and the irrational number. Everyone knows that rational number has a numerator and denominator. Numerator is also whole number, the denominator is also whole number, and we can represent the rational number as a ratio. We can represent it as a ratio of the 2 whole numbers, so it is a rational number. And for the irrational number, we cannot represent it as the ratio of the 2 whole numbers, like root 2, root 3, these kind of things, and which are also very common in geometry, because the diagonal of a square is root 2 of the length of the side. So root 2, root 3, these kind of things will come largely in geometry. But while we will talk about the algebra, then we can make it simpler if we take 6 decimal places, or if we take 11 decimal places and then divided it with the number of decimal places, 10 to the power number of decimal places, then it is a pure whole number kind of things. And we are doing with approximately any irrational number is also a rational number approximately. We can think it in that way, such that we can geometrify it, and then later on we can proceed it with the much more rationalization functions and all those things. That is the later on cases. But first we have to consider the things such that the computational model can algorithmically design the geometry out of any given trigonometry expression. First thing first, because this system was not at all there even the large language model is appeared, still this kind of functional programming on trigonometry expressions is not yet there. So we have to make it first, and first we have to make the computational models for these, and after the things will run, then the research will go on, and we will get many kind of procedures to handle these rational numbers in geometrifying trigonometry. That is the second part of the research. Now we are not going to bother that much with that. Now the point is a very small unit, very small structural unit of geometrifying trigonometry, and point don't carry any right meaning for anything. But line segment is a very interesting object. You all know that vectors don't have the division operations, but in geometrifying trigonometry there is a very well defined model for all the functional operations like plus, minus, into, divide. All of these are applicable on line segments only. Again I repeat that the most fundamental operational structural unit of geometrifying trigonometry is a line segment with the 4 different symmetries. And the functional unit of the geometrifying trigonometry is also a line segment. The line segment takes everything. When 2 Gtsimplex are added, we ultimately add the whole Gtsimplex in such a way that alignment of 2 output line segments of the, suppose Gtsimplex 1 is added with Gtsimplex 2, then obviously the Gtsimplex 1 has an output line segment, and Gtsimplex 2 has another output line segments. And when the 2 Gtsimplexes are placed one after another in such a way that the output line segments of 2 Gtsimplexes are aligned or are placed one end to another end of another line segment, then it is added, and there is a huge jungle of entangled line segments will form, and that is the addition. For the multiplication cases, one Gtsimplex is multiplied with another Gtsimplex is done with the align and scale to fit. There is a separate video on that. The multiplication is doing. In that case, one Gtsimplex is aligned in such a way that the input line segment of the second Gtsimplex is scaled, aligned, and fit with the output of first line segment, first Gtsimplex, and in this way the multiplications are done. For the division cases, that is the interesting subject. When we divide one line segment with another line segment, that means the line segments are output line segments of 2 Gtsimplexes or the output line segments of 2 locked set, and ultimately they form a triangle. The output and the input are placed in this way. Suppose the input line segment is like this, and it is at the denominator, and the output line segment is at the numerator, and they are placed in this way. So input line segment, output line segment, and a third line segment is added, which is the complementary line segment. Like this, they are added to form the complementary line segments, and in this way the triangles are formed. This is the concept of division. So you have understood that how the plus, minus, into, divide works in case of Gtsimplexes or in case of the locked sets. So plus, minus, into, divide, all of the things are ultimately done with the output line segments or input line segments of the objects. Either these objects, either the line segments are output line segments for Gtsimplexes, or either they are the input line segments of Gtsimplexes. They interact with each other. For multiplication cases, the gluing is multiplication. Gluing is the align and scale to fit, and in this process the multiplication of 2 Gtsimplexes is done, or the multiplication of 2 locked set is done. I should tell a simple word for the locked set here. Suppose sin alpha cos theta plus cos theta tan alpha plus cos gamma sin alpha, these plus things are done, and this is a locked set. Ultimately, when 2 ratio are multiplied, then it is a Gtsimplex, and when multiple Gtsimplexes are added, then it becomes a locked set. Whatever it is, there are the output line segment. Ultimately 3 line segments are added consecutively, and it is forming a longer line segment, and this longer line segment is the representative for the locked set, and this longer line segment is coming from a common unit given line segment L, capital L, and this capital L is generating the Gtsimplexes, and these Gtsimplexes outputs are taken and aligned and then made a longer line segment, that the whole jungle of line segments in the different Gtsimplexes conglomerate together with the output line segment, and this whole bunch of line segments which are entangled with each other. This whole thing is called a locked set, but ultimately the locked set interact with another locked set through the output line segments only, or with the input line segments, or with the output line segments. And for the case of Gtsimplexes also, they interact with each other with the output line segments only. When we do the plus and minus, the output line segments are the most important thing. This is the axiom of geometrifying trigonometry. For the case of the plus or minus, the output line segments of Gtsimplexes or the output line segments of the locked sets interact, and when they interact, they don't forget the other line segments. They carry all the jungle of entangled line segments in the locked set or in the Gtsimplex all together with them, and then only the output line segments are aligned, but all other line segments also remain present on the 2D plane. They are not vanished, they are still there. So whenever anything changes, the whole thing changes, and whole picture jumbles, and many different kind of geometric shapes come out. There is a separate video 2-3 days back I have made on these different kind of jungles which change their shapes and sizes when the seed angle changes. I have already demonstrated that for half an hour, so you can check that, so that you will understand how the things are dynamically changing. For the plus and minus cases, the output line segments are fundamental, but for multiplication of two Gtsimplexes or for the multiplication of any locked set, the input line segment comes into the play. How? The output line segment of first Gtsimplex is of same or aligned and scaled to fit with the input line segment of the second Gtsimplex. We should talk it differently. That is, in the separate video of multiplication is gluing, you will find in Google, if you search the multiplication is gluing, you will get the complete story of how we consider the multiplication in geometrifying trigonometry. There you will get that the multiplication, division, plus minus into divide, all of the things are non-commutative. I repeat, plus minus into divide, all the functional process of operations in geometrifying trigonometry are done geometrically. So all of these are non-commutative but associative. They follow distributive law, but they don't follow commutative law. And that is because while we do multiplication, the input line segment of second Gtsimplex, when suppose we are multiplying Gtsimplex 1 with Gtsimplex 2, if Gtsimplex 1 is on the left side and Gtsimplex 2 is on the right side, then obviously you have to understand that the input line segment of Gtsimplex 2 is scaled and aligned to fit the output line segment of Gtsimplex 1. Similarly, when two locked sets are multiplied, we have already said that every locked set also have a initial line segment and a final output line segment. So when any locked set is multiplied with another locked set, suppose the locked set 1 is kept on the left side and locked set 2 is kept on the right side, and they are multiplied, then the input line segment of locked set 2 is aligned and scaled to fit with the output line segment of locked set 1. That is the definition of multiplication of locked set. Similarly, a Gtsimplex is multiplied with locked set, or locked set is multiplied with Gtsimplex. Whatever we do, the operation of multiplication is not commutative. Obviously, that for division also the commutative law never holds for the number systems also. I repeat again that real numbers, all real number is a triangle, and all triangle is a real number. So we can have the structural and functional property of the real numbers is isomorphic, almost isomorphic to the geometrifying trigonometry. Only one kind of thing is different, that is nothing is commutative. Another thing very important here is every operator plus minus into divide has a 4 symmetries. So at every abstract syntax tree deductive mechanisms, at every stages of the plus minus into divide, wherever we will see that, we will have to take 4 pictures at every operator. That means it's a huge tree, huge deduction tree will come out whenever we solve any trigonometry expression. These are the conditions due to which trigonometry expressions were not geometrified up to 2022. That is, for 3300 years, this subject was kept dumb because all these intricacies and were not done, and we cannot expect that all these things will come out before the computational systems was there, because who will draw so many number of the pictures on the pen and paper, and obviously for after second power or the third power the pictures either becomes too large or the picture becomes too small. Without the CAD programming we cannot expect that this kind of images you can generate, because without computers we were not in the right place. The mankind was not mature enough to generate all such pictures, and until machine learning systems was there, it was very robust to handle for any human mind, because at every stage of deduction it is generating 4 symmetries. Again, for another operator it is generating 4 symmetries. So the syntax tree, the deduction tree, is a very large tree. It is not like the ordinary arithmetic, it is not like the ordinary algebra that you will get only one deduction tree like thing and that you will easily handle it in mind. It is not easy to handle on mind, and it is ultimately hard work, because you have to draw so many large number of pictures, and ultimately drawing the pictures with ruler, compass and measuring the things is very tedious work. Until the CAD system was mature enough, we could not expect that this kind of subject will come up. And obviously I repeat that it is just 1880 the vector algebra came out. At 1843 quaternion came out. Matrix algebra got matured from 1880 to 1920, and you should not expect, no one can expect that computational model will come out before these kind of things were done. It's a long journey. After these giants made all these platforms ready, and when the machine learning platform is also ready, now it was possible for a CAD programmer like Sanjay could generate this axiomatization. But otherwise, if all these platforms was not ready, it was very tedious to think about these kind of subjects could ever come up. Now we have already explained that every functional interaction is done through line segments, and either it is input line segment or it is output line segment or it is a complementary line segment. The most fundamental functional unit of geometrifying trigonometry is obviously a triangle, because all interaction is done through the triangles. So after division a triangle is formed, and triangle is also a simple form of Gtsimplex, and it is also the simplest form of any locked set. Similarly, the line is the most functional unit of Gtsimplexes and for the locked set, but the structure will break until we handle triangles there. If we want to do multiplication or division, we cannot think the process until we take the line segments as a triangle, because the align and scale to fit work and only work if we take the triangle as the most fundamental functional unit. So these are the fundamental talks on which we will now explain what do we mean by the structural concepts and the functional concepts. And the concept of the structural property and functional property are often used to describe different aspects of any object or any system or any concept. Structural property the structural property refers to the inherent characteristics or features of the object that define its physical or organizational structure, or that is the data structure with which we will do the programming. And I have already explained that why triangle is taken as the functional unit of the organizing, and we have already made another video, and there is a blog site on which we have explained the data structures there. And in automated trigonometry simulator in Autodesk forum you will get the data structure there, and you can refer it in C# to make your own EXEs for machine learning systems, and there the data structure is already defined very well, and the blog link is also given in the comment box. From there you can get the idea of the data structure which is used in this concept of geometrifying trigonometry. So the data structure is the will handle the structural property, which refers to the inherent characteristics or features of an object that defines its physical or organizational structures, and it describes the arrangements, compositions, or relationships between the components or elements within the objects. The structural properties are concerned with the object's form, shape, connectivity, the spatial organizations, and these things are already explained just now, so I am not repeating those part again. For example, if the context of a building or its the structural property would include the arrangements of the beams, the columns, walls, and roofs, and determine its stability, the load bearing capacity in a data structure, and the structural properties define how the data is organized, such as in a linked list or in a binary tree. But here we use a quad tree because at every operation we have the 4 branches coming out. I have made a separate video on that, and you can refer that also. Now we are trying to describe the overall the meaning of the functional properties. The functional property, on other hand, relates to the proper purpose, behaviors, or roles that an object or the system fulfills. Geometrifying trigonometry has a role to play. It will expose the geometric behaviors of the triangles which are hidden inside any trigonometry expressions. It is a glued form of triangles. It can give us a triangulated diagram like the Delaunay triangulation. It can give us the Voronoi diagram kind of diagrams. After parsing the geometry expressions or after parsing the trigonometry expressions or trigonometry identities, it will show the nature of similarity, like if the 2 triangles are similar, then 2 ratios are equal. It can show in that way. Or if the line segments, if 2 different line segments are having same length, that is also a property of identity. If 2 angles are same, then also it can call it as the functional equality. So the definition of equality is also a functional property for any object. We have defined the different conditions in different axioms to compare to Gtsimplex or to compare to locked set objects in the geometrifying trigonometry, that we will come in the later videos with the examples for the exercise books from the trigonometry exercise problems from different examinations and from the different textbooks, so that you will understand how to think anything as a Gtsimplex or when to think it as the locked set. We will come up with those things in the later videos. Now, the functional property, we are continuing with the functional property. The functional property focus on what the object does or how it behaves in a given context. Suppose there are 2 or 3 different trigonometry expressions and all of these are valid, then we will try to examine how many parallelograms are forming or how many points are aligning in such a way such that they are all concentric, or we will try to examine how many parallel lines are forming or how many similar triangles are forming in the jungle of line segments in the Gtsimplexes or in the locked sets. Those kind of functional queries that we do on the problems of Gtsimplexes or on the locked sets in the geometrifying trigonometry, these kind of problems are never inquired before geometrifying trigonometry. We have solved many trigonometry expressions, we have solved wave equations, we have found several quantum states, but we have never ever asked this kind of questions on the jungles of entangled line segments and what are the geometric graph theory like properties hidden inside any trigonometry expressions. We were not inquiring on these kind of questions ever. Now for instance, in the case of the car and its functional properties encompass its ability to transport people, accelerate, decelerate, steer on the stop. In the software, the functional properties of a program describe its intended behavior and the tasks it can accomplish. Here in geometrifying trigonometry, our intended problem statements are to inquire the geometry from the trigonometry expressions. We will not try to solve the trigonometry expressions just to get the value of an expression as a number, or we are not going to try to find any pure number as the length of some line segment. We are not bothered with these small kind of problems in geometrifying trigonometry. These kind of small problems are already solved in normal ordinary trigonometry. In geometrifying trigonometry, we are trying to understand the nature of entanglements of the line segments due to the construction properties of these computational geometry. It is better to tell it as a computational geometry form, and which is automatically parsing trigonometry expressions which generate the triangulated mesh kind of things, and from where we are inquiring several deep properties hidden inside these mesh kind of objects, or the simplex kind of objects, or the locked set kind of objects, which are geometry, purely line segment arrangements, the geometry which looks like bridge, or which looks like the town planning, or which looks like any map on the 2D plane, or the like on the 3D plane, or like any car networks, or as a telephone networks, or as a circuit diagrams, or as a VLSI chipboard. We can think these kind of pictures are there coming from any trigonometry expression. Just imagine. And now you can have several optimization problems on that, like you do on the network problems or on the graph theory problems. That kind of inquiry you can get from the trigonometry expressions, which you have never thought ever before 2022, and before Geometrifying Trigonometry parser came out, and before the automated trigonometry simulator was there in the Autodesk forum. Before the Sanjana's Geometrifying Trigonometry was there, you could not expect these kind of inquiries coming out from any trigonometry expressions. These are the functional inquiries actually we are trying to say in this video. In summary, the structural properties are concerned with the physical or organizational characteristics that define the object structure, and here the objects are like line segments, triangles. Triangle is also the simple form of the Gtsimplex, or the triangle is taken as a simple form of a locked set, or Gtsimplex is a object here, object of concern, and locked sets are also the objects of concerns. Now another big deep object of concern is the definition of equality. There are several layers of equality that we discuss in case of Geometrifying Trigonometry. The two line segments are exactly overlapped, then it is the best form of equality. Sometimes the direction of the line segments, so consider it like a vector, or sometimes left to right, or sometimes right to left. All of these kind of overlaps are not, sometimes crisscrossed, sometimes they are perpendicular always for all values of theta. These kind of inquiries are very deeper kind of inquiries which we can ask to a geometric object, and we cannot ask this kind of geometric questions on a trigonometry expression. Obviously the trigonometry expression is like algebra kind of thing. It is not exposing the geometric behaviors of the line segment, so how can you ask these kind of questions to any non-geometric entity? You can ask a geometric question to a geometric entity only. You cannot ask any geometry kind of questions from an algebra kind of object. Obviously in the coordinate geometry also, equation of a circle, until it is well defined that it is this kind of equation is a circle's equation, and until it is formalized, how can you ask a question of a circle to an equation? It is formalized in that way after Fermat made it, and after Descartes made it, then only these equations are turned into the pictorial objects. But this kind of exercise was never done for trigonometry kind of things. So from a trigonometry expression, you could not ever expect that how many triangles are forming there. You could not expect that what is the nature of the triangulations forming there. So how could you ask the geometric questions to these trigonometry expressions? Now you should become happy that in Sanjana's Geometrifying Trigonometry, you are getting some way, you are getting some light to generate and automatically generate in the CAD diagram to get the scaled drawings from the trigonometry expressions in the CAD file, such that you can ask, at least you can make a machine learning model, you can make a TensorFlow model, or you can make a PyTorch model on that, such that you can ask the deeper geometric questions to the geometric objects that is generated from parsing the trigonometry expressions. And that parsing is also generating large number of pictures because of the quad tree nature of the syntax tree. Obviously we have already shown in another video, and from where you can check why the quad tree forms. Now we are trying to give an analogy that is a metaphorical kind of thing, but analogy, and that will help you to understand the nature of these. And in previous videos also I have explained, and here also I have said that all real numbers are triangles and all triangles are real numbers. Now I should tell you the structural and the functional properties of the real number system, such that you can connect the triangles with the real numbers, and you can make a mindset that yes, we can ask more deeper questions on geometrifying trigonometry, such that you can expect deep on geometrifying trigonometry. I also expect that in Sanjana's Geometrifying Trigonometry there is a large number of inquiries possible, and which were not ever done on the trigonometry expressions. How? Because I should tell you the real number system is a fundamental mathematical construct. It's a construct like a data structure, and that encompass all relational and irrational numbers. And when considering the real number system, we can discuss the structural properties and functional properties. Like the structural properties of the real number system refers to its inherent characteristics that define its organizational and properties, and these properties include the ordered structures, that is the numbers are ordered, like 2 is greater than 1, 3 is greater than 2, in this way. The real numbers are ordered, meaning that the numbers can be arranged in a meaningful way. In the same way, we can ask is two Gtsimplex comparable? Yes, if the output line segment is long of any Gtsimplex is longer than the output line segment of another Gtsimplex, then we can compare them in this way, because all the Gtsimplexes in a given trigonometry expressions are generated from a single line segment L. So we cannot compare the initial line segments. The initial line segments are all the exactly same line segment. All Gtsimplexes for any given trigonometry expression are generated from a single line segment L. So we cannot compare with that. We can compare with the output line segments. We can compare with the number of the line segment jungle forming inside any Gtsimplex. We can compare with the number of line segments present in a locked set. We can compare with the number of Gtsimplexes are involving in a locked set. How many locked sets are multiplied together to generate the large number of Gtsimplexes entangled with the multiple number of the entangled line segments. We can compare the number of line segments overlapped due to the process of forming of the Gtsimplex or due to the forming of the locked sets. We can ask these kind of several questions, and we can make the comparison between the Gtsimplexes, and we can make the comparisons with the locked sets. And so comparative property is also an inherent property for any numbers, and for Gtsimplexes and for the locked set cases also. And arrangement of the meaningful way along the number line, and the order allows for comparing the comparison operators such as the greater than or less than or equal to. These things are very important objects of understanding for the structuralness, the structured nature of any number systems, and for any geometric systems like the Gtsimplexes or locked sets or triangles or line segments, and there the comparisons is necessary. The algebraic structure and the real number system has the well-defined algebraic structural structures, including the operations such as the addition, subtraction, multiplication, and division. Okay, here also in this video I have already described the plus, minus, into, divide are all well defined for the Gtsimplexes, for locked sets. And we can take the cos theta plus sin theta plus tan theta whole to the power 6. This is a sixth power of a locked set. It is not the sixth power of a Gtsimplex, because the plus are there, like cos theta plus. This plus is not allowed in the Gtsimplexes. This plus is allowed only in the locked set. So for if we used to say that cos theta into cosec theta whole to the power 6, that means the cos theta into cosec theta is okay, it is a Gtsimplex, because two factors are multiplied, no plus is there inside, so it is a Gtsimplex. Suppose we can take it as a cos theta plus sin theta whole to the power 6. In that case, this plus inside the cos theta and sin theta is making it a locked set. It is not a Gtsimplex. And when the sixth power is done, then it is a Gtsimplex made up of the locked set. So the Gtsimplex formed from locked set is a different kind of algebraic calculation, and locked set made up of Gtsimplex is a different kind of construct. So understanding these kind of constructs is also very important thing, and in our next video we will talk about the more deeper parts of these constructs, and we will start from the completeness and the functional properties and the arithmetic operators with the different structural and functional properties in our next videos. But up to now, I think it is sufficiently clear to you that how we are organizing the whole data structure such that automated machine learning systems can generate theorems, such that the automated computational model can generate the CAD files in scale. It can generate the SVG animations, SVG to the scale files from any given trigonometry expression. That will help anyone to understand. Mainly that will help the engineers. The students will get help later on, but mechanical engineers, civil engineers, structural engineers, road planning, the engineers, the surveyors, or the people who are doing programming for the GPS systems, they will get benefited fast, because trigonometry is more used for these kind of professions. And even for the jewelry designers, even for the designers who work for the CNC systems, even for the people who work for the manufacturing or for the satellite positioning or the engineers who work for the jewelry design or for fashion designing or for shoemaking, they use trigonometry too much to make the leather cuts or other kind of manufacturing processes. They will get benefited before, because they see any trigonometry expression, then they try to generate the pictures out of that before the manufacturing process starts on. Even if you have seen any fabrication process in the steel industry, you will see the cutting plans of the plates or the cutting plans of the objects are done using the trigonometry expressions. First the engineers convert it into geometry and then they do the processing. So you should not tell that the students will get benefit first. The real benefit will come into the industry, the manufacturing industry, and that was the fundamental motive. Sanjay was developing these things because Sanjay was working on this kind of industry and he was developing the softwares for this kind of industry, and he was facing large number of problems for 20 to 22 years, and to process the trigonometry expressions manually, then drawing the pictures manually in CAD, and after that he could prepare the CNC files. So he understood the problems there, and so he was working hard to find some computational model. He was trying to understand the structural units of these trigonometry expressions. He was trying to understand the functional units of these trigonometry expressions, such that the CNC files can generate automatically from the trigonometry expressions, such that he can generate the bridge designs out of the trigonometry expressions directly. This could help his professional programming systems, and for that reason he was developing this. The students will get the benefit obviously because they can get the visualizations, and the researchers will get the benefit because they can ask the geometric questions directly to the geometric objects. The graph theorists and the network analysts also will get more benefit because they can explain the whole adjacency matrix or the incidence matrix directly with the trigonometry expressions, and the geometric graph theory will also get large benefits due to these things, because the Gtsimplex or the locked sets ultimately look like the graph-like objects, and with the vertices, with the edges, and obviously you can understand that any triangulated graph is ultimately a graph-like object. So in the next video we will come up with the additional parts of the structure and the functional properties of geometrifying trigonometry. Thank you. We will continue with more details later on.